Okay, so I'll be giving the introduction of maximize. So what does it mean by maximize? Maximization refers to the process of finding the highest possible value of an objective function within a given set of constraints. So on the left side, Z is for the objective function. For example, profit. X and Y are the decision variables. And the last one, constraint indicate limited resources such as time, labor, raw material, and others. Okay, so on the right side, maximize objective. Z equals to K1X plus K2Y. Constraint A11 plus A12Y less than or equal to B1. A21 X plus A22Y less than or equal to B2, and XY equals to 0.
Assalamualaikum warahmatullahi wabarakatuh. My name is DAIM NIZAM, and today I will going to present on the case study linear programming by graph maximum problem. Starting with the question itself. During COVID, Dollah learned to bake while on home quarantine. He also realized that he will be able to make 60 ringgit profit per tray of banana muffins and 120 ringgit profits per tray of blueberry muffins. He needs 2 cups of milk and 3 cups of flour to bake a tray of banana muffins. And baking a tray of blueberry muffin takes 4 cups of milk and 3 cups of flour. He has 16 cups of milk and 15 cups of flour. How many trays of each flavor must he bake to maximize the profit? Okay, for the key question of this case study is how many trays of each muffins should Dollah bake to maximize his profit without exceeding his resources. Okay, the next part is solve the problem on maximum linear programming. Starting is let's define our decision variable, which is we let x as the number of trays of banana muffins, while y as number of trays of blueberry muffins. The objective function is to maximize the profit, and to be exact is to maximize the profit per tray, and the method is by z equals to 60 ringgit x plus 120 ringgit y. To identify the constraint, starting with non-negative constraint, which is x is bigger than 0, y is bigger than 0, while for per tray of banana muffins and blueberry muffins need 2 and 4 cups of milk, which is Dollah has only 16 cups of milk, is 2x plus 2y is lesser than 16. And the next one is for the next calculation, which is 3x plus 3y is lesser than 15, is that per tray of banana muffins and blueberry muffins needed 4 and 3 cups of flour, which is Dollah has only 15 cups of flour.
Okay, now let me present the overall model summary of this linear programming problem. Our main objective is to maximize monthly earning, which is represented by the objective function. So this is a z equal to 60x plus 120y. This means for each tray of banana muffin that summarized as x, we earn 60 ringgit, and for each tray of blueberry muffin, which is y, we earn 120 ringgit. So our goal is to find the combination of x and y that give us the highest total earning. However, we cannot produce because the limited trays. Okay, and then we are limited by sources such as milk and flour. These limitations are called constraint in linear programming. Okay, we move to the first is we have a mid constraint that is 2x plus 4y equal or less than 16. This means banana muffin require 2 cup of milk per tray and blueberry muffin require a 4 cup. The total milk available is only 60 cup. Next we have the flour constraint, which is a 3x plus 3y equal or less than 15. Banana muffin need a 3 cup of flour and blueberry muffin also it need a 3 cup per tray with only 15 cup of flour available in total. Another condition we include is a x equal or less than y. This might be a business decision to ensure we always bake a more or equal tray of blueberry muffin compared to banana muffin. And, of course, in any real world situation, x and y must be greater than or equal to 0. This simply means we cannot produce negative tray of muffin.
Next, I will be presenting a part of the linear programming model, which is a fundamental topic in operational research. Especially, I will explain the main question line, which is represent one of the limitation in a linear programming problem. In linear programming, we often deal with a constraint that are written in the form of linear inequalities. For the example, we are given a constraint that 2x plus 4y equal or less than 16. To graph this constraint, we first need to convert it into a equation for the boundary line. 2x plus 4y equal to 16. Then we find the intercept so we can draw the line on the graph. On the left box, we are solving for the x-intercept by setting y equal to 0. Substitute y into a 0 into the equation so that we get 2x plus 4 times 0 equal to 16. Next, 2x equal to 16 and we get x as 8. So the intercept of x is at 8.0. On the right box, we solve for the y-intercept by setting x into a 0. Substitute x into a 0 into the equation. So we get 2 times 0 plus 4y equal to 16. Next, 4y equal to 16. That means y get a 4. So the y-intercept is at 0.4. Okay, moving to the graph on the right, we can see the straight line connecting the two intercepts. This line represents the boundary for the constraint 2x plus 4y equal or less than 16. The shaded region below the line show all the feasible solution or the combination of x and y. Okay, after that I will explain the flow question line. For this problem, we are given a constraint 3x plus 3y equal to 15 and 3x plus 4y equal to 15. Okay, to graph the constraint, we first need to convert it into equation for the boundary line. Then we find the intercept so we can draw the line on the graph. On the left box, we are solving for the x-intercept by setting y equal to 0. Substitute y into a 0 in the equation. Okay, so we get 3x plus 3 times 0 equal to 15. Next, 3x equal to 15 and we get the x as 5. So the x-intercept is at 5.0. On the right box, we solve for the y-intercept by setting x into 0. Substitute x equal to 0 in the equation. So we get 3 times 0 plus 3y equal to 15. 3y equal to 15 and we get the y as 5. So the y-intercept is at 0.5. Moving to the graph on the right, you can see the straight line connecting the two intercepts. This line represents the boundary for the constraint 3x plus 3y equal to 15 and 3x plus y equal to 15. Okay, the shaded region below the lines show all the feasible solution or the combination of x and y.
Okay, Assalamualaikum. My name is Muhammad NAJMI bin AZRIN. So I will present about optimization analysis for the max muffin problem. So we start with defining our variable, which is x be the number of tray of banana muffin bake, and y be the number of tray of blueberry muffin baked. So for the calculation linear equations, you start with 2x plus 4y equals 16 and 3x plus 3y equals 15. Next calculation is 6x plus 12y equals 48, 6x plus 6y equals 30, 6x 6y equals 18, and y is 3. So the next one is next calculation is 2x plus 4y equals 16, 2x plus 4 in bracket 3 equals 16, 2x plus 12 equals 16, 2x equals 4, and the last answer is x equals 2. So we get 2 is x and 3 is y. So we already do the maximum. X is 2, then maximum y is 3 units. Okay, so for the next slide, which is corner point and option solution. So next, look the possible corner points for our feasible region and calculated the objective function at each point. Our objective is to maximize the revenue given by the function. And as you can see in these calculations, corner point 0, 4, x is 0, 4 is y, which is z equals to 60, bracket 0 plus 1 to o, bracket 4, then, equals to 480. So 2 for the next corner point is 2, 3, 2 is x and 3 is y, z equal to 60, bracket 2 plus 102, bracket 3 equals to 480. So the last one is 5 is x and 0 is y, which is z equals to 60, bracket 5 plus 1 to o, bracket 0, and bracket 0, and equals is 300. Okay, for based on the optimization analysis, the maximum revenue of 480 ringgit is achieved at 2 points, which is the first one is baking 2 trays of banana muffin and 3 trays of blueberry muffin, or baking 0 tray of banana muffin and 4 tray of blueberry muffin. This means Dola should either make no banana muffin and 4 tray of blueberry muffin, or 2 tray of banana muffin and 3 tray of blueberry muffin using 16 cups of milk and 15 cups of flour. So that's all for me for this section. I will pass to the next presenter.
Okay, so for the introduction of minimize, minimize is integrals consists of all positive whole number, negative whole number, and zero. For example, on the left side, we can see 0, 1, -1, -5, and 18 are integers. And on the left side and on the right side, 1/2, 2.3, 1/3, 3.14, and -4.7 are not integers. Okay, that's all from me.
Okay, moving on towards the next part, which is case study linear programming by graph minimum problem. Begin with the question. This time, our immune system is the best defense. With this, Aziz wishes to mix two types of food in such a way that vitamin contents of the mixture contain at least 8 units of vitamin A and 10 units of vitamin C. Food A contains 2 units per kilogram of vitamin A and 1 unit per kilogram of vitamin C. Food B contains 1 unit per kilogram of vitamin A and 2 units per kilogram of vitamin C. It costs 50 ringgit per kilogram to purchase food A and 70 ringgit per kilogram to purchase food B. The question is that how many kilogram of each food should Aziz include to minimize the cost? while meeting the vitamin requirements. Okay, to solve the problem, starting with the decision variable. So we let X as the number of kilogram of food A, while Y is the number of kilogram of food B. The objective of the function is to minimize the cost, so it is to minimize the cost of food mixture, which is Z equals to Rm50X plus Rm70Y. While for the constraint is to let 2x plus 1y is more than 8, which is mixture vitamin A constraint, while x plus 2y is more than 10 is the mixture constraint for vitamin C. And x and y is bigger than 0, it is non-negative, and also the integers as well. Technically, the minimum cost is Rm380 ringgit, and to achieve this, when Aziz uses 2 kg of food A and 4 kg of food B to meet all of nutritional constraints.
Now let's look at the mathematical model we developed for this problem. Our objective is to minimize the monthly cost, which is represented by the function z equals to 50x plus 70y. Here, x and y represent the quantity of two different mixtures. To ensure the mixture meets nutritional requirement, we have the following constraints. First, vitamin A requirement is 2x plus 1y is greater than or equal to 8. This ensures the total mixture contains at least 8 units of vitamins. Second is vitamin C requirement is x plus 2y is greater than or equal to 10. This guarantees a minimum of 10 units of vitamin C. Third is proportionality constraint, which is x is less than or equal to y. This indicates that the amount of mixture x must not exceed the amount of mixture y. Fourth is non-negativity constraints. X and y must be greater than or equal to 0. This is standard in linear programming to ensure that we are not working with negative quantities. These constraints, our goal is to find the value of x and y that minimize the cost of z. Let's begin by looking at our first constraint line, represented by the inequality 2x plus y is greater than or equal to 8. To graph this, we first need to find where the line intersects the x-axis and the y-axis. To find the x-intercept, we set y equal to 0. Substituting y equals 0 into the equation, we get 2x plus 0 equals 8, which simplify to 2x equal 8. Solving for x, we divide both sides by 2 and get x equals 4. So our x-intercept is the point 4.0. Now let's find the y-intercept by setting x equal to 0. Plugging that into the equation, we get 2 times 0 plus y equals to 8, which simplify to y equals 8. That gives us the y-intercept at the point 0.8. These 2 points allow us to draw the boundary line for the inequality. On the right side of the slide, you can see the graph with the line connecting 4.0 and 0.8. The shaded blue region shows the area that satisfies inequality 2x plus y is less than or equal to 8. All the points in this region make the inequality true, and this becomes the part of our feasible region when solving the linear programming problems. Now let's move on to adding a second constraint to our graph. This time we're working with the equation x plus 2y equals 10. As before, we start by finding the intercept to help us draw the line. First, for the x-intercept, we set y equals to 0. Substituting into the equation, we get x plus 2 times 0 equals 10, which simplify to x equals 10. So the x-intercept is at the point 10.0. Next, for the y-intercept, we set the x equal to 0. Plugging that in, we have 0 plus 2y equals 10. Dividing both sides by 2, we get y equals 5. This gives us the y-intercept at the point of 0.5. On the graph to the right, you see the new constraint line drawn in pink going through the point 10.0 and 0.5. What's important here is the new shaded region. It's overlap with the earlier blue region we saw on the first slide, and this overlapping red area is now our feasible region.
Okay, so the minimum cost of mixture, the calculation linear equation is 2x plus 1y equals to 8, 1x plus 2y equals to 10. So the next calculation is 2x plus 4y equals 20, 2x plus 1y equals 8, 3y equals 12, and the last answer is y is 4. So next is a 2x plus 1y equals to 8, 2x plus 1 bracket 4 equals to 4, equal to 8, 2x plus 4 equals to 8, 2x equal to 4, and the last answer is x is 2. So we got it 2 for x and 4 for y. So maximum large room is 2x for 2 units, and maximum large room is 3 units. For the corner point of optimization, optimal solution, your corner point is 0, 4, z equals to 60, bracket 0 plus 1 to 0, bracket 4 equals to 480. So 2, 3, z equals 60, bracket 2 plus 1 to 0, bracket 3 equals to 480. So 5050, z equal to 60, bracket 5 plus 120, bracket 0 equals to 300. So based on our linear program analysis, the minimum cost represented by Z is 380 ringgit. This occurs when 2 units of food A and 4 units of food B are combined. So importantly, both volume of X and Y are not zero, meaning that both of types are essential and achieving the nutritional requirements. So with the combination of Aziz is able to meet at least 8 units of vitamin A and 10 units of vitamin C to fulfill the dietary constraint. So therefore, Aziz will spend 380 ringgit per mixture by using the optimal blend to ensure the nutritional at the lowest possible of cost. So that's all for me and from us. Thank you.